Okay, so we've got our group action. Oops, group action, which maps G cross X to X, and we see that Gx equals Y. That's how we write it. Where G is a member of G, X is a member of X, and the group action G acting on X sends it to Y, where Y is a member of X. And we also defined an equivalence relation. We proved it was an equivalence relation, and we said X is related to Y if there exists G in the group such that Gx equals Y. And we showed that that was transitive and symmetric and all the rest of it. So it's a equivalence relationship, and we defined different orbits O1, O2, O3 and O4, and X was related to Y if X and Y were both in the same equivalence class, either both in here or both in here, and not related if they weren't. So, and we call those classes, we call them orbits, or sometimes G orbits. Okay, so what do they look like? Well, I'm going to choose a group of matrices that look like this. They're going to be of the form cos theta minus sine theta cos theta. Okay, and you'll recognize these as rotation matrices. What they do is, on two-dimensional plane here, they take a point X, and if you apply this matrix to it, if that's equal to the matrix M, let's say, and theta equals, let's say, 10 degrees or something, then what this matrix will do is take this point X and it'll rotate it round clockwise by 10 degrees to get X dash, where X dash equals MX. Sometimes while I'm writing I'll put a little twiddles like that, it's not a twiddles, it's just an underscore to tell you that it's a vector, and sometimes I'll put 2 underneath M, underneath a matrix. I should put 1 there, I guess. 2 underneath there, just to remind myself that it's a matrix. I haven't seen anybody else use that notation. Well, not for a long time anyway, but that's what I do. So these rotation matrices, and of course, well, you can verify for yourself it's a group. What's the group action? Well, I'm going to take my set X to be just R squared. That's my set X, set of points on the plane. There it is, I've got my little axes set up. So there's my X, and my group action, I'm going to define Gx. Remember here that G is a member of my group, my set G in my group, and X is a member of R squared here, because X is capital X is R squared. So I need a definition, and of course I'm going to say that equals, well, I'm going to write it slightly differently. I'm going to say Mx equals, well, Mx. It's kind of a bit obvious really when I write it like that, Mx equals Mx. But what I mean to say is that my group action is just regular matrix multiplication. Regular matrix multiplication. Okay, so what do my equivalence classes look like? Well, here's my set X and Y. Here's my ground, my set X. So X is my set R squared, and I'm gonna have slightly different colours here. Just a minute. I'm going to use blue. Here's my point X. So if I multiply it by a matrix here where theta, where are we? By this one here with theta equals 10 degrees. Well, I just rotate it around there. So that's part of my orbit, and it should be obvious that I can rotate it by any angle right round here. And of course that goes for sets point, this might be point Y here. So my orbits are concentric circles. Green, I think that's the only colours I've got. I might have one more. Grey, here we go. That's supposed to be concentric circles. So that's quite a nice little image to have in mind, I think. So the orbits of the plane under G and the group action which corresponds to regular matrix multiplication are concentric circles. And I think that's quite nice. I'm going to stop right there.